All right, for this next video, we're going to be studying nuclear chemistry, which is how the chemistry of changing nuclei really works. And so this is the foundation for nuclear energy. There's certain different approaches that we're going to need to use to follow nuclear equations, because this is something that we really have strayed away from in chemistry so far, really focusing not how the nucleus might interact, but on how protons, electrons, and how atoms will join together and whatnot occur. That's really the realm of classical chemistry. Furthermore, we're going to look at the kinetics of nuclear decay and learn about what the rate of these nuclear reactions may be and how this can inform us about certain things like the age of a species through a process like carbon dating, or really the dating of any other type of radioactive isotope. All right, without much more, let's go ahead and jump into the video. So the first thing to understanding nuclear chemistry compared to classical chemistry that we've been looking at for the most part previously is that now we're going to be dealing with changes to the nucleus. You know, before we've seen lots of reactions where we'll have bonds forming, bonds breaking, basically atoms that are joining together or breaking apart. We've had electrons that are coming and going. We've had protons that are coming and going, but we've never really broken the nucleus in any of the things that we've studied so far. But this does occur. This is really a jumping off point for this whole branch of nuclear chemistry. And we can show, for example, the following, right? Where we have a neutron that's colliding with this uranium containing 235 total protons and neutrons. It's becoming an unstable nucleus and then breaks into two smaller nuclei along with a few stray neutrons. And we can show how these reactions will occur with the following notation at the bottom, right? We show that it's a uranium plus a neutron. It's coming together for just a moment into a 236 proton and neutron containing species, and then breaking up into a barium, a krypton, and 3 neutrons. How we keep track of these nuclear reactions, very important to show the isotope itself, so the number of neutrons that are available, and we will be able to keep track of all of this matter as shown in the bottom. Okay, so again, when we have a nuclide, this is a specific radioactive particle, right? So really just a certain nucleus. When this nuclide decays, it's going to form daughter nuclides of lower energy. So it's going to form new, atoms, so to speak. But we really don't want to call these atoms because they are not really taking into account the electrons, right? The electrons matter, but when we're looking at these nuclear equations, we're not really taking into account the electrons that honestly may or may not be there depending on how the reaction is going. So when we have a decay process, we want to show this by a balanced nuclear equation. And in this case, we're not balancing the elements, which is something that we really based our study of chemistry on previously, that we have the same number of oxygens on each side, same number of hydrogens, and all of that. What we must balance on is the total mass. And so what we see here is that we have these isotopic symbols where we have the letter A in the top left and the letter Z in the bottom left. And the total of that A value has to be equal to the total of that A value on the product side, right? Reactants and products. And this must be true for the total of the Z value, which is the number of protons as well. So maybe give this one a little look here, right? We have a uranium that's turning into something plus a helium, right? On the one side, we have 238 total protons and neutrons and 92 protons. And the helium has 4 protons and neutrons and 2 protons. So what's missing here, right? What does this uranium become as it's losing this helium nucleus? And the answer is it's going to become this thorium, where we have 234 total and 90 are the number of protons. And we can look at the top numbers, right? On the left side, the top number total of protons and neutrons, the mass, if you will, is 238. And therefore, it must be 238 on the other side, and the number that makes that work is 234. Same is true for the protons. 92 total on the reactant side means that this unknown, which turns out to be thorium, is 90. And how do we know it's thorium? Well, because it has 90 protons. 90 protons means thorium. Thorium means 90 protons. We get this from the periodic table, and this is always true, right? The number of protons defines the name of the species. Again, we can plot this out as a little table here. The sum of the mass numbers has to be the same on each side. The sum of the atomic numbers must be the same on each side. And this is how we got that answer of this thorium-234 here. Some of these decay processes are relatively common, right, and should be known and, just will need to be known because they're sort of the naturally occurring decay processes. And when we're thinking about these decay processes, what we want to focus on is the particle that's going to be jumping off from this nucleus. So the first of the particles is the alpha particle. This is a helium nucleus, so 2 protons, 2 neutrons. The next is a beta particle, so it's just an electron, right? It's got no mass and it's got a charge of -1. We also want to look at a positron, so this is kind of a weird particle, but it's like a proton but positive, so +1 charge, no mass. A proton here we can say is a 1,1 hydrogen, right? It's a 1 charge, +1, and it's got a total mass of 1, so a proton. We want to deal with a neutron. This matters as well, right? 1 and 0, so 0 charge but a mass of 1 is a neutron. And a gamma ray, which does not have mass or charge. It's just high energy electromagnetic radiation. And these matter because we want to track the following different types of decay. And the first is alpha decay, and basically what occurs here is that we have an alpha particle, a helium nucleus, 2 protons, 2 neutrons, that leaves. Beta decay is a beta particle leaving, so we have an electron that's leaving. And what occurs here for this electron leaving is that a neutron is actually turning into a proton, right? The neutron has this package of negative charge which it's shooting off, and so what we're left with is a mass of 1 with a charge of +1 because it's lost that electron, and that's a proton, right? The total mass is not changing, the charge is increasing by 1. And this may seem like kind of a lot right now, but we're going to kind of see in the next slide how this is all somewhat relevant. Gamma decay is the next thing that occurs, and this is for if we have some sort of excited nuclear state. And I think the easiest way to envision this is like after alpha decay, we've lost this big chunk of matter. There's this big hole in the nucleus. And the nucleus doesn't like this. It wants to rearrange into a more uniform sphere. And to do so, it needs to release some energy. And so the gamma particle is what may be released for this case. Positron emission, electron capture. Hopefully these are kind of making sense how this works now. Positron emission, we're losing a positron, so this is a proton turning into a neutron. Electron capture, it's an electron joining with a proton to make a neutron. In each of these cases, the Z value or the charge is going to decrease by 1. And so this is sort of the change that occurs, right? Alpha decay makes the whole thing smaller. Beta decay brings the charge up. Positron emission, electron capture, that brings the charge down. And the idea is that different radioactive isotopes have certain origins of their instability, right? Some of them have charge that's too high. Some of them have a size that's just too large. And it will naturally get back to a stable nucleus by undergoing one of these named decay processes. So we can plot this out using what we call the band of stability, right? And what we basically have here is on the bottom axis, we have the number of protons, right? So we start off with really small elements, so hydrogen, helium, oxygen, etc. And as we move up, we have the larger elements. And if we see the line in blue, right, which is we see gets kind of up from a balance of a 1-to-1 ratio of protons and neutrons, number of neutrons, that's what's on the y-axis, that's our stable, right? Those are our stable nuclei. And you've probably seen this already, right? That when we have very small things, they tend to have a mass that's about double the atomic number, right? Oxygen has an atomic number of 8 and an atomic mass of about 16. But as we get larger, we end up needing a few more neutrons to compensate, right? It's slightly more than double the atomic number. And that's where we prefer to be, right? That's the stable, non-radioactive version of that isotope. If we end up having slightly more neutrons or slightly fewer, there's an instability, and it's going to want to get back to a regular state, right? It's going to want to get to a non-radioactive state. And so that's what this band of stability shows, is that in green we have the ones that have a bit too many neutrons or a bit too few neutrons and may need to undergo one of these decay processes. Also, if we're just too large, so we'll notice that the blue on this band of stability kind of breaks off after 83 protons. If we have more, it'll always want to be smaller. It's just too big to be stable, and so those are always radioactive. Those are going to want to undergo alpha decay. That's what makes the nucleus smaller. And if we have too few neutrons, then we're going to undergo the positron emission or the electron capture because that's forming another neutron. And if we have too many neutrons, which is much more common, then we're going to want to undergo the beta decay, and that's going to create, one less neutron. The cause of the instability, again, will determine the decay process, and we can see sort of the origins of that based on this graph, which is relatively common when starting out looking at these nuclear reactions. The other thing we want to think about is what are the kinetics of radioactive decay? And if we recall from our kinetics video, first order is a common form of decay. And basically what this says is that it's going to decay based on the amount that's present. And what this also means is this idea of half-life applies, where if we have 10 grams of a species, it becomes 5 grams in one half-life. Then after another half-life, which in this case we'll say is 5.27 years, after the first 5.27 years, we go from 10 to 5 grams. After the next 5.27 years, we become 2.5 grams. And so after that duration, we divide in half. This is characteristic of first order kinetics, and we can use this relationship between half-life and the K constant to demonstrate that relationship. If we have the half-life, we can calculate the rate constant K, and with the rate constant K, we can solve for different concentrations of interest. A key area that this is of interest in is in carbon dating. So perhaps you've heard of this before. When an organism is living, it has a certain naturally occurring amount of carbon-14, which is a radioactive but safe isotope. And over the course of 5,730 years, a sample of carbon-14 will divide in half. That's its half-life. So if we can detect the amount of carbon-14 that's present in a species and compare that to the amount that's present in all living organisms, including us right now, we can say, well, it's got half of the amount that it should have if it was living. Therefore, it must be 5,730 years old, right? One half-life has passed because it's showing half of the amount that it used to. And so therefore, we can calculate the age of the species, which will require us to get the rate constant as well. So again, mathematically, if we want to know the age of the species, the first thing we want to do is say, well, the half-life is equal to the natural log of 2 over k. This is just a rearrangement of our integrated first order rate law, and by just saying, what if we have half left? With this, we can get the amount that's present at any time, or given the amount that's present, we can find out the age that it's been. So what's an example of this? This is the equation that we're going to use. What if we have the following, right? We have a piece of charred bone that shows a C14 disintegration rate of 9.2 and then the following units, right? And we want to compare this to the rate of disintegration in living organisms at 15.3. And so basically, if we have 100, let's say, C14, it's going to be disintegrating at such a rate. If there was only 50 of them, it would be disintegrating at half the rate. And so this is one of the beauties of this decay process being first order, is that if we know that the rate is half, that means there's half left. And so, in other words, even though we're looking at decay rates here, because that's really what you use to detect how much C14 is there, how much you detect is decaying currently, we can really treat that as if it's just a quantity, if that kind of makes sense, and that's based on first order decay. So go ahead and pause the video here, see if you can solve this one. The first step is going to be calculate that K value based on the half-life, and the second is going to be using the integrated rate law to use K to find the age of this species. All right, hopefully you were able to give this a shot. First thing, again, is we want to solve for K. So K is equal to the natural log of 2 over the half-life. I've just rearranged the equation in the bottom left. And we end up with a K value of 1.21 times 10 to the negative 4 per year. And so again, right, the half-life is just the rate constant that's kind of recast into a more easy to conceptualize variable, right? The time it takes to divide in half. But mathematically, we need this K value to solve the integrated rate law, which we can do. We say the natural log of the initial amount of decay, which is 15.3, minus the natural log of the current amount of decay, 9.2. K applies, we have T, we have an equation in one variable, and we can see that this T is equal to 4.2 times 10 to the 3 years old, or 4,200 years old. And I think it's really good to assess our answer here, right? Because how much is left, right? We've started at 15.3, we've ended at 9.2. This is slightly more than half. In other words, it hasn't quite divided in half yet. And so if we look at the answer we've come up with, 4,200 years, that kind of makes sense because after 5,730 years, it will have divided in half. But we haven't waited quite that long yet, and our answer makes sense. I think when working with logs and these type of equations, if you get an answer that says 5 million years, that doesn't seem in relation to the half-life. And if you got one that was like 0.002 years, that also doesn't seem quite in relation either. So taking your answer in context, very important for solving these half-life equations. All right, that is our introduction to nuclear chemistry. I hope it has shown a slightly different look at the chemistry topic, and I look forward to discussing more in the next video.